For this project, we each took questions related to biomechanics from orthobullets.com and attempted to explain them in a brief presentation. The next question that we will look at states, in the stress-strain curve, the irreversible change in length after removing the load during the plastic range is called. The correct answer to this question is plastic deformation. But why? To answer this question, we are going to look at the aforementioned stress-strain curve, where strain is represented on the x-axis and stress in pascals is on the y. Each of the terms for the question can be highlighted on this graph. The first term we see, the proportional limit, is shown to be at the end of the linear portion of this graph. It is defined as a transition point between elastic and plastic deformation, or the highest stress, at which stress is directly proportional to strain. For many metals, the proportional limit is equal to the elastic limit, which is defined as the maximum pressure, or stress, that a piece of material can withstand without being permanently deformed. The last point on the graph, the breaking point, is defined as the point at which the object fails and breaks, which is obviously represented here on this graph where the curve ends. The ultimate strength, or the load to failure, is the maximum value of the bending force, which is shown to be the highest point of the curve on the graph. So what about the last term, plastic deformation? As you can tell by looking at the graph, there is an elastic zone and a plastic zone. When a load is applied that remains in the elastic zone, like this line here, the process of loading and unloading follow the same path, resulting in an object that is the same after the load is removed. As you can see that this line here ends back in its original place, demonstrating a reversible change in length. This is known as elastic deformation. When a load is applied that continues from the elastic zone, following the curve into the plastic zone, the deformation has exceeded the elastic and proportional limits. When this load is removed, the material follows a different path, and the material after deformation is no longer the same shape as the original material, shown by the difference in position along the x-axis. This irreversible change in length is known as plastic deformation, answering our previous question. The next question that we will look at asks, the amount of energy per volume that a material can absorb prior to failure defines which of the following terms? The correct answer by definition of the word is toughness. The toughness of a material is defined as the work per unit volume required to fracture material. Thus, it can be used to measure material's ability to absorb energy without fracturing. A visual and mathematical representation of toughness is the area under the strain energy, or stress-strain curve, is illustrated here. Therefore, it can be mathematically determined by taking the integral of the stress-strain equation to find the area under the curve. The simplest form of the curve is shown here, a linear graph plotting stress versus strain. The area of this curve is defined as the area of a triangle, so the toughness of this theoretical material would be 1/2 stress times strain. This graph also defines another answer choice. The equation of this line relates stress and strain and also gives us the slope of the line, represented by E. This value is known as Young's modulus, which measures the stiffness of a material, and knowing this definition, we can eliminate it as incorrect. In the previous question, we defined the breaking point to be the point at which the object fails and breaks, or the last point on the graph. This is also the definition of the failure point, one of our answer choices for this question, that we can now identify as incorrect. The last two terms are illustrated here, and they are wrong by definition as they deal with different properties of materials. Viscoelasticity refers to the property of a material that exhibits viscous and elastic deformation and a loss in energy when returning to the material's original shape. Fatigue strength deals with cyclic properties and is defined as the highest stress that a material can withstand for a given number of cycles without breaking. Therefore, we can conclude that this question does in fact define the toughness of a material, and we can eliminate the other answer choices by understanding their definitions.